The webinar will consist of a brief overview of SERDP and ESTCP, followed by the technical portion of the webinar, featuring research on advances in remediating groundwater contaminated with chlorinated solvents. We'll start off with Dr. Steve Richardson from GSI, who will present on an innovative application of a geotechnical technology, the Grout bomber, to improve the delivery of remedial amendments at sites with low permeability media. Steve's presentation will be followed by a brief Q&A session. Dr. Greg Devine will then discuss an in-situ remediation concept, the horizontal reactive media treatment well, for controlling long-term mass discharge at contaminated sites. Craig's presentation will also be followed by a Q&A session, and we will conclude the webinar with a longer session involving both of our speakers. On this slide, we have provided a few suggestions in case you experience difficulties with the broadcast platform. Firefox, IE, or Edge are the most compatible browsers to use. If you lose the content on your screen or if your screen freezes, try keying Control and F5 to perform a hard refresh. If you are accessing the audio through your computer, click the arrow next to the Join Audio button, select Test Speaker and Microphone, and follow the prompts as they appear on your screen. If you do continue to experience difficulties, please call into the conference line shown here. You may also submit a comment using the chat box. Please use the chat box only for comments related to technical difficulties. The Q&A option should be reserved for questions for the speakers. Today's broadcast will be listen only. You may submit questions by using the Q&A box on your screen. You do not need to wait until the Q&A period to submit your questions. We do encourage you to submit questions well in advance of those sessions. Just remember that when you submit your questions, please add your organization name at the end of each question so that we can identify you during the Q&A sessions. With that, I would like to introduce Dr. Andrea Leeson, who is the Deputy Director of SERDP and ESTCP, as well as the Program Manager for the Environmental Restoration Program area. Dr. Leeson has been with SERDP and ESTCP since 2001, and before that, she served as a research leader at the Battelle Memorial Institute, where she conducted scientific research on in-situ bioremediation and the design and implementation of innovative biological, chemical, and physical treatment technologies. Andrea received her doctoral degree in environmental engineering from the Johns Hopkins University. Andrea?
Thanks, Rula, and thank you everyone for being here today. I think you'll really enjoy the two webinars or two presentations we have today as part of this webinar. Next slide. Before we get into the heart of the webinar, I'd like to give a little bit of an overview about who we are and what we do in these two programs. We are comprised of these two sister programs, the Strategic Environmental Research and Development Program, and that's really our science and technology program. It's a partnership actually between the Department of Defense, Department of Energy, and the Environmental Protection Agency. And what we work on is developing fundamental to applied research so that it impacts these real world environmental management issues that we have. ESTCP, which is the Environmental Security Technology Certification Program, is our demonstration and validation program. And often what we see is that the knowledge or the technologies that are developed under SERDP will mature and progress into ESTCP, where we can demonstrate the technologies in the field. And what we really work on is transitioning those technologies out of the lab in the field, where we can establish the cost and performance and really develop knowledge that the end user can use to implement these top technologies at their site. Next slide. So we have two main broad drivers for our programs. The first is sustaining our testing and training ranges, as well as our facilities and operations. That is very broad, as you can see from the different topics that are listed here, everything from maritime maritime sustainability, noise issues, sustainable forward operating bases, UXO, et cetera. So very broad environmental drivers. Next slide. And then we're also looking at reducing current and future liability at our installations. This can take the form of dealing with contamination from past practices, as well as pollution prevention so that we control life cycle costs. And the presentations you'll hear today are ones that are dealing with contamination from past practices. Next slide. Next slide. So we really work hard at the technology transition, and that really comes at the end of these ESTCP projects so that the knowledge and the information that's gained from the technologies gets transferred to the end users in an appropriate way. So we have a lot of different ways we do this, and all of these items are found on our website, from different videos, guidance documents. We have a special Wikipedia sort of a site called our EnviroWiki that summarizes a lot of these technologies. And then, of course, we have this webinar series that we put together to highlight different demonstrations that are coming out of the ESTCP program. Next slide. If you go to our website, in particular, this link that's listed here, you'll be able to see a list of all the webinars that are coming up in 2020. That information will be up soon, but you can also see an archived list of all of the webinars we've given since the start of this program. So it's a really valuable resource. Next slide. So at this point, I'm going to turn it back over to Rula to introduce our next speakers.
Thank you, Andrea. It is now my pleasure to introduce our first speaker for this webinar, Dr. Steve Richardson, who is a principal engineer with GSI in Austin, Texas. Steve specializes in the application of innovative strategies to treat conventional and emerging contaminants in soil, groundwater, and surface water at a wide variety of contaminated sites. He has served as a principal investigator on several DoD-sponsored research projects involving the cometabolic biodegradation of 1,4-dioxane, innovative approaches for the treatment of chlorinated solvents in low permeability zones, anaerobic bioremediation strategies for DNAPL, and most recently, PFAS treatment. Steve received his doctoral degree in environmental engineering from the University of North Carolina at Chapel Hill. Steve, please proceed.
Thanks so much, Rula. I appreciate the introduction, and thanks to ESTCP for the opportunity to share our results with you all. Before I start, I'd like to acknowledge my co-principal investigator, Chuck Newell, for his contributions to this project. As Rula mentioned, the title of my talk today is the new application of a geotechnical technology, and that's the Grout bomber, to remediate low permeability contaminated media. On slide 2, for today's talk, I'll walk through the following: a problem statement, technology description, field demonstration, performance results and operational considerations, some conclusions, and then benefits to the DoD. So we move on to slide 17. The problem statement. So let's start with what we know about the problem. We know that difficult to treat sites are increasing as a percentage of total DoD chlorinated solvent sites. And that's happening for a couple of reasons. These middle stage sites, and these are sites that where dense non-aqueous phase sources are active, are transitioning into these later stage sites where we're starting to see matrix diffusion sources dominating. And so what this ends up causing is sites that have high life cycle costs and often very long remedial timeframes. And so what we're really looking for are these innovative and inexpensive technologies that will address the matrix diffusion that we're seeing from these low-K source zones, as well as enhance the treatment of contaminants leaving those low-K source zones. So let's move on to slide 4. the geotech industry. Why not? They get to play with some pretty big pieces of equipment. The geotechnical industry offers a variety of well-established techniques for quickly and efficiently accessing the subsurface for the purposes of ground stabilization, foundation rehabilitation, pore water drainage, as well as structural support. It's the speed and efficiency of these techniques that's advantageous to our field, to the environmental field, particularly for the emplacement of remedial amendments. Two promising techniques with potential environmental applications are the wick drain installer as well as the grout bomber. Both of these techniques offer rapid access to the subsurface at depths well beyond 50 feet. We investigated both of these technologies as part of this project, but ultimately decided to focus our efforts on the grout bomber for a variety of reasons, which I'll get into, not only because of its really cool name. So on slide 19, we'll talk about the grout bomber and simply the bomber. It's a direct push technology that delivers cement grout into subsurface voids to displace and increase the stability of surrounding soils. So in essence, it's not only just filling voids, but it's squeezing native material together to increase the stability for foundations or for above ground infrastructure. The specialized stitcher machinery, it involves a mandrel, which is a cylindrical rod that is pushed to depth, and it pumps high viscosity grout into the surrounding voids as that mandrel is raised from depth to the surface. And the benefit here is that you can get hundreds of these grout columns being installed per day with spacings as close as 2 feet. And so being a direct push technique, the bomber is most appropriate for silts and clays, mainly with blow counts below 35, and then materials with higher water content. So we're able to, again, push this mandrel down, this 3.5-inch column, push it down to depth, and then bring it back up in a rapid manner. We can also deal with consolidated materials that have blow counts that are greater than 35, but that may involve some pilot hole drilling as well as some additional equipment to handle that. Slide 20. So how does the bomber work? The typical equipment arrangement for the bomber includes the installation rig, the excavator with the stitcher mast, and an on-site grout mixing and delivery unit. So generally that includes an Elkin mixer, which is on the left panel, a hopper and a positive displacement pump that is in the center panel, and then that moves us over to the excavator and stitcher mast, which is what the grout bomber is. Aggregate cement powder and water are batch mixed in the Elkin mixer, which is then delivered to a hopper and positive displacement pump. The mixture is then pumped through hosing to the top of the stitcher mast, and it's delivered to the subsurface once the desired depth is reached. For our application, the mandrel, or that cylindrical rod that is attached to the stitcher mast with 3.5 inches in diameter and 40 feet in length. So the important point here is that our goal is to create our own amendment grout, and in this case using zero-valent iron, oil, as well as some sand, and to repurpose the bomber to deliver the amendment mixture. Slide 21. So let's move over to our technical objectives, which was to install very, very closely spaced, this is 2 to 3 feet, reaction columns for the goal of shortening contaminant diffusion pathways. We also wanted to improve subsurface amendment delivery. In other words, we want to get as much amendment as we can in the ground as quickly as we can. And then we also wanted to create these hundreds of vertical reaction zones to degrade chlorinated volatile organic compounds, or CVOCs, with the goal of shortening that long tail that we see from back diffusion that we'll see on those concentration versus time graphs. Slide 22. So the technology description side of things, I wanted to drive this point home, which is one of the limitations of traditional drilling is that the time it takes to install injection points, as well as the uncertainty of the amendment delivery once it enters the subsurface. So without fracturing techniques, only a small percentage of the low K zones typically at that interface are exposed to the amendment. And so if you look at the right panel here, we're typically putting in injection wells on the order of 10 feet apart up to 30 feet apart in many cases. The majority of that material, the amendment material, goes into those high K zones, with very little of that material actually contacting the low K interfaces. In our application, on the left panel, that's the Grout bomber technology, we're creating these closely spaced vertical reaction columns without injecting material into the subsurface. So we're not trying to get it into any of the higher K zones or pushing it outwards. It's simply to create these vertical columns with the goal of increasing the surface area of those low K zones that are in contact with the amendment. So again, this is not an injection, or at least this application of the bomber is not an injection technology, more of an emplacement. So our goal here is to emplace hundreds of these closely spaced vertical reaction columns. Slide 23. Further, by creating these closely spaced reactive zones, which is the goal of the project, we're generating this concentration gradient. So lower concentrations in the reaction columns versus higher concentrations in the native material, which is going to drive diffusion of CVOCs that are trapped in those low K zones. So that's what's shown on the left panel here. You can see if you zoom in, what we're trying to create is this diffusion front. So the concentrations within the native material stay high. As you approach that interface, they drop, and you get these lower concentrations that are in the reaction columns. On the right, as a proof of concept, we performed a simple model where greater than 100 milligrams per liter of TCE was loaded into the clay zone, and that's shown in red. And under the M&A scenario, most of the contamination remained after about 20 years of the model run. Whereas when we installed these zero concentration or low concentration zones at 2 foot spacing or 2 foot center spacing, we were seeing these significant reductions in TCE. You can see that red starts to turn to orange and turns to yellow. So we're driving or changing that concentration gradient, driving transformation of TCE from the clay and reducing concentration that we would see in any sort of down gradient wells. So that glide path in the M&A only scenario might be pretty steady, whereas in the reaction column scenario, we're hoping for a much more steep or gradual decline in the glide path of a C versus T plot for any sort of monitoring well that may be in the area. So again, the key point here is that we're generating these concentration gradients that will drive diffusion of contaminants into those reaction zones. So we move over to slide 24. The last point here on the technology description is that we're really relying on these abiotic and biotic reactions to maintain that concentration gradient between the reaction columns and the surrounding native material. Abiotic degradation of TCE generally follows a beta elimination pathway, and that's shown if you follow the pathway from your zero-valent and TCE across to a chloroacetylene, down to acetylene, that follows that beta elimination pathway. And the benefit there is that we can look for those intermediates as proof for that the abiotic degradation pathway is active at the site. There's also a biotic pathway, which we're all familiar with, which is the TCE biologically degraded down to cis, vinyl chloride, and then down to ethene. So our goal at this site is to see as much ethene and ethane as we can, and to, again, drive that material that's trapped in low K zones towards those reaction columns for production of these intermediates as well as end products. So on slide 25, we're going to talk a little bit about the field demonstration. And this happened at Site 17, Naval Support Facility, Indian Head in Maryland. And this the site was previously used for disposal of metal parts, as well as other pieces of equipment were disposed there over time. And over time, this ended up growing. There was a whole bunch of growth, a lot of vegetation. And so as part of this demonstration, we had to do some clearing to identify this source zone, as well as do some work at it. Depth to groundwater of about 5 feet below ground surface, for fairly shallow. The treatment area consists of silts, sandy clays, and lean clays, some fat clays at depth down to about 30 feet. And so this was an ideal site for us to test whether we could actually make any sort of difference in terms of the CVOC concentrations from a site that is predominantly low K material. TCE concentrations were very high, up to about 400 milligrams per liter in one location. And contamination extends to about 30 feet below ground surface, as I'd mentioned. We also saw concentrations upwards of 250 milligrams per kilogram in soil within that treatment zone at a depth of about 15 feet. And the size of the treatment area is fairly small. Our focus was on the area representing that 1 milligram per liter contour, which you can see in that sort of light blue in that box there, which is about 4,700 square feet, or about 1/10 of an acre. So moving on to the slide 26, we'll talk a little bit about what we did at site 17. So on the right-hand side, you'll see the same image. This is again the 1 milligram per liter and 10 milligram per liter contours with the existing monitoring wells also shown. And what we installed was 800 reaction columns over a period of about 7.5 days. And those columns are represented by these small dots that you're seeing. So we had closer spacing within the 10 milligram per liter. That was about 2-foot spacing. And then as we moved away towards the limits of this 1 milligram per liter contour, we extended the spacing to about 3 feet. But by and large, with this type of a piece of equipment, it was anywhere from 2 to 3 feet, just depending on where we were located within the treatment zone. Again, these columns are 3.5 inches in diameter, spacing 2 to 3 feet. Of the 800, 700 were ZVI and sand reaction columns. So those consisted of 40% ZVI and 60% sand. And then an oil was added to improve some pumpability of our amendment mixture, so to make it a little bit more slick so we could get it through some of the hosing up to the top of the excavator. The remaining 100 were strictly oil and sand, so no ZVI was added, at a 40% oil to 60% sand mixture. And that location, so the location of those oil columns was up in the sort of northwest zone, close to monitoring well 16 as well as CMT 4. I will also point out that we also added these CMTs, and I'll talk about those in a couple of slides. But they were added as a means to monitor or look at concentrations within a reaction column and compare those to an accompanying monitoring well. So if we could see that concentration gradient or that difference between the reaction column concentrations as well as the neighboring monitoring well. So slide 27 talks about how do we know that this technique is going to work. And as I mentioned, the CMTs were installed directly in the reaction columns. And so it's an added benefit of the bomber is that we can actually install something within the reactive media. And we do that using a technique called bottom feeding. So in this case, the CMT well was fed up the mandrel, or the cylindrical rod. It was attached to the base with an anchor plate. And then the mandrel was pushed to depth as it was for all the other 800 reaction columns. And ZVI was filled around the annulus of the CMT within that mandrel. So once at depth, the mandrel was lifted, the ZVI material filled that void space as it was moving upwards, and it created a CMT well within the reaction column, which is pretty cool. The screens at those CMTs were set to 5, 15, and 25 feet. As I mentioned, the majority of that soil contamination existed within those intervals. And so we were interested to see if there was any vertical distribution of contamination from, again, that 5-foot interval down to closer to the base of that treatment zone, which was at 30 feet. So if we move on to slide 28, we can talk a little bit about the operational results. Again, as I've mentioned, the 800 columns were installed over about 7.5 operational days. And I say operational days because we did have some weather delays that were in between, but it was a 2-week field demo. And again, 7.5 of those days we were actually operating. And so we were able to put in that number of columns to a depth of 30 feet. And again, they're 3.5 inches in diameter. We were averaging, once we got going, to about 100 columns per day. One of our best days, which was one that made me smile, was 180 columns that were installed to 30 feet in one day. If you do the math, it works out to about a column being installed every 2 to 3 minutes, again, during our peak operation. We added vegetable oil, which was not our original plan, but it was a backup in case we had issues pumping a ZVI sand and water mixture. So we did add a little bit of vegetable oil, which served a couple purposes. One is a binder for that pumpability, but also is going to serve as an electron donor in the subsurface. So essentially these columns are abiotic columns with a touch of biotic, so to speak. We've emplaced, during the field demonstration, 77,000 pounds of ZVI and about 650 gallons of vegetable oil. And if you do the math, it works out to about $38 per cubic yard of treated material, which includes the labor, equipment, as well as the ZVI and the sand that we used in the field demonstration. And again, if you look on the picture on the right, again, that's the excavator, which is a standard excavator, 350C excavator with the stitcher mast, which again extends to about 40 or 50 feet, and the mandrel goes from top down to the bottom. So move on to slide 29. We can talk a little bit about performance assessment to date. And what I'd like to do is focus on individual CMT and monitoring well pairs. And what I've done here is plotted the CVOC concentrations in molar concentrations, so we can look at that total mass of CVOC over time within the CMT that's closest to this monitoring well, which would be CMT1, as well as what's happening in monitoring well 4. So in terms of the y-axis, that's concentration, again, in molar concentration, as well as our dates of sampling, which extended from July of 2017, which is when we installed these columns, all the way to October of 2019. And what you'll notice that we see is gradual trend, decreasing trend in CVOCs. The proportions of CVOCs may not be changing a whole lot, but we are seeing sort of a gradual decrease in TCE. The biggest take home here is that the concentrations compared between the CMT1 as well as MW04 are about an order of magnitude difference. So we're seeing this bigger difference between the CMT and monitoring well, which suggests we're getting this concentration gradient between these monitoring well and CMT or reaction column chemistry. The last point I want to make in this slide is that acetylene was in fact detected. We're getting some low levels, ppb levels of acetylene being detected in CMT1, which gives us some direct evidence that abiotic reactions are occurring in the subsurface. And our second performance slide, which is slide 30, we'll skip over to the oil area. These are only just the oil and sand reaction columns, and we're seeing, again, pretty promising results, gradual decreases in CVOCs over time in the monitoring wells. And you'll notice that the change in concentration, or the difference in concentration between the CMT4 as well as MW16 is in this case on the order of 2 to 3 orders of magnitude different. In the small inset that's in the CMT4 graph, you can see that's that change in concentration within the reaction column. So again, we're seeing different proportions of daughter products showing up, but again, concentrations are much lower in the CMT than they are in the monitoring well. And again, just to drive that point home, the CMT and the monitoring well are only about 2 to 4 feet apart. So if we skip over to slide 31, we'll just provide some supporting evidence, and then we'll move into some of the closing remarks. And so there's some supporting evidence here. We've installed 2 soil vapor probes installed in the unsaturated zone of a couple of the reaction columns. And what we've found is we've found some higher coupling products that have been detected, again, in that unsaturated zone. These include propane, as well as butane, propene, a variety of others, which again suggests that we're seeing this abiotic TCE degradation pathway that is occurring. this transformation of TCE into these higher coupling products. Another supporting line of evidence, and this sort of, we came upon this almost by accident, was duplicate sampling from the CMTs. And so we're sampling the pore water from these CMTs. We're only doing very limited purging and collecting what's in that sort of pore space within the reaction column. And what we tend to see time and time again is this smaller concentration during the first sampling, and then when we sample a duplicate almost immediately after, the concentrations generally get higher. So if you can imagine, we're removing water from the reaction column, and we are, and then water from the formation or from these low K zones are moving in, which would have a higher concentration of CVOCs. Moving into slide 32. Just the overall performance results. Again, as I mentioned, we had a gradual TCE decrease in monitoring wells. Again, minor fluctuations in some of the daughter product concentrations. The big take home here is that the CVOC concentrations at the CMTs are on the order of 1 order of magnitude up to 3 orders of magnitude different than the accompanying monitoring wells. And we see that throughout the other CMT monitoring well pairs. That is, again, evidence of a concentration gradient. And we do see biotic and abiotic mechanisms occurring, the presence of acetylene in a couple monitoring wells as well as the CMT. We see increases in cis and vinyl chloride and ethene. And then the production of these higher coupling products as well gives us some more supporting evidence that we're actually getting degradation of TCE occurring in the subsurface. If we move over to slide 33, we can talk a little bit about operational considerations. Again, before using a technology like this, we need to understand what we're getting involved in. The bomber requires vegetation clearance. It requires some surface conditioning, so that needs fairly level surface. And it requires about a full day of setup in order to get that mast set up onto the excavator before you can actually do any of the work. The mast can achieve depths of greater than 50 feet. That can be customized. Our geotechnical contractor is able to make different depths. And then it's appropriate for silts and clays with low counts that are less than 35. A couple of points: that the site must be well characterized. There's a higher risk for DNAPL and source zone issues. Again, we're creating vertical columns, and so this is a transport pathway. So you need to understand your site's geology before you move forward with a technology like this. And another improvement is that we're putting material from top to bottom at this site. It would be better to be able to actually place the material within the treatment zone. And so we can do that with some modifications to the equipment. And slide 34, we'll talk a little bit about take-home messages and then wrap up the webinar here. So 800 reaction columns were installed, 1 reaction column every 2 to 3 minutes. Biotic and abiotic degradation products were detected. We've got some low treatment costs on the order of 38 bucks per cubic yard, which is similar to what we're seeing for bioremediation, as well as some of the lower end costs for chemox. And then it's a promising and cost-effective alternative for delivering these remedial amendments. And on the last slide, we'll talk a little bit about the benefits to the DoD. This serves as a long-term treatment option for CVOCs. It's a great treatment option for matrix diffusion sites from what we're seeing so far at site 17. It's suitable for a variety of different contaminants and remedial amendments. And then lastly, there's some other applications. Again, we could use these for sand columns to enhance aerobic treatment. We could use it potentially for supply wells, for electrokinetic technologies, as well as passive subsurface reactors and simple permeable reactive barriers. And I'll wrap up with some acknowledgements. I'd like to appreciate all the help from the Site 17 personnel and contractors and folks from the Navy. Of course, ESTCP for the funding and the opportunity to test out this technology. And then the GSI project team, Dylan Hart, Justin Long, Mike Schofield, as well as Chuck Newell, and Hayward Baker, Josh Colts, who was responsible for the reaction column installation. We also did some geophysics work, which I wasn't able to present in the time we had here. Stuart McDonald and Todd Hallahan on that. And then the Rice University kitchen, which helped us pick between the wick drain installer and the bomber earlier in the project.
Thank you so much, Steve.
Oh, you're very welcome.
Yeah. So we received a lot of questions for you. As a reminder, you can go to Steve's project's webpage on the SERDP ESTCP domain, and you could download the final reports and other relevant information from that webpage. At this point, we're going to turn over to Q&A. And as a reminder, you can submit your questions by using the Q&A box on the screen. We've got a number of questions for you, Steve. So we're going to start off with the first one here from Clemson University. What is the lateral effectiveness in the delivery of amendments using the grout bomber technique?
What is the lateral effectiveness? Is that right, Rula?
That's correct.
I'm assuming what you mean by that is, are we seeing distribution of material outwards from these columns? And if that's the question, if I'm understanding it correctly, again, the goal is to maintain these columns for the purpose of this application as a vertical column. We wanted to prove as a diffusion-based technology that this could occur. In other applications, you can actually push the material out into a higher K zone, and that you would see a lateral distribution. In terms of the whole site itself at Site 17, again, it's a very small site. We were more interested in the mechanisms, whether we could achieve that diffusion-based technology, which was the focus of comparing the CMT to the monitoring wells. But overall, we're not seeing a big change in the overall mass at this point. Again, it's only been a couple years. We have some follow-on work with the Navy where we'll be looking at this as a long-term performance or technology, or the long-term performance of this technology at that site.
Thank you, Steve. This is a question from the Connecticut Agricultural Experiment Station. Do you think that TCE could partition into the oil droplets and cause the immediate reduction of concentrations that you've observed?
Yes, absolutely it could. And so that's always a possibility. And that's the importance of doing long-term monitoring. So as that oil ferments and degrades, you'd expect to see this increase in concentrations. What we generally are seeing since the installation within the CMTs is initially a gradual increase, which you would expect because we had water that was added to this mixture, but then a steadying of concentrations over time. So the possibility or that mechanism of TCE partitioning into oil is possible, but not from a long-term standpoint as that oil would degrade.
Thank you, Steve. This is a question from Oregon Health and Science University. Can you comment on the differences in degradation results as a function of depth?
We have looked at that, although right now we have the monitoring wells are screened. I think they're about 10-foot screens. And so we have the only depth discrete intervals that we've got are from the CMTs, and those are 5, 15, and 25. So at this point, we do see in the CMTs changes in concentrations and depth, but that's strictly because the treatment zone is a reflection of the mass that's in the zones at depth. So we're seeing higher concentrations at the 15-foot interval across the board and lower concentrations at 5 and 25. What is interesting is that we are seeing increases in some of the ethines and ethanes over time in those more shallower zones in the CMTs, which may reflect this migration of these lower or smaller hydrocarbons that are moving upwards in the column. But in terms of comparison from monitoring well to CMT, it's difficult to do given that the monitoring wells are screened 10 feet across that same interval.
Thank you. During your demonstration, is it possible that the vegetable oil consume the zero-valent iron?
Unlikely. We added a very small amount, and so I didn't really disclose. Again, 650 gallons that we added, that was primarily to the oil columns. Again, 40% oil and 60% sand. In terms of lubricating the ZVI mixture, we added, I think per batch, it was on the order of like a gallon. A very small amount of oil was added. So I would be very surprised if the oil, in fact, was impacting the ZVI reactivity. I think this is a diffusion limited site, and so the slow degradation that we're seeing is a reflection of mass transfer from low-K zones into the reaction column.
Great. And this is a question from the Washington State Department of Ecology. Have you done any modeling or other assessments to see how long the restoration time frame will be?
Yes, well, we're going to. So the answer is no, but yes. So we are, that's the next stage. And I mentioned that we're doing some work, follow-on work with the Navy at this site. And that's one of the questions that we're trying to answer, is to give them an idea of the remedial time frame for this site. If we went to the proof of concept model, again, the goal of this technology is not to clean up the site within a year or two. This is closer to 10 years on that range. We know that ZVI can last upwards of 10 to maybe 20 years. There's some indication that it can extend longer. And so our hope is that we can see a glide path and model something where we can get an idea as to how long the time frame will take at this site. So that's still to come.
All right, and this is a question from the Army Corps of Engineers in Baltimore. Could you implement this technology using one of the larger direct push rigs?
You could. I mean, so a larger direct push rig, the difference between this technology and what we're seeing out in our industry, and maybe some of the geotech vendors or the vendors that we use may have a better answer than this, but generally what we were noticing with the geotech technology here is that they're able to push, they have a lot more force being able to push down. And so again, we've done a lot of work installing injection points, and in some cases I've installed injection points up to 10 or 20 a day, but never have I seen something that can access the surface, subsurface in the range of 100 to 150 columns a day. So I think it could be done, but there may be some retrofitting that needs to happen on some of the equipment that we're currently using.
Great. Would you expect better biotic or abiotic results over 2 years than achieved within the columns with CMT monitoring?
That's a difficult question. I think given that this was, I would expect to see better ZVI, just because we've focused our efforts on that remedial amendment. One of the things I didn't mention was that there's an accompanying plume that's at the same site. That's the south plume. This is the north plume that we were working on. The south plume has had some soil mixing work done that involved a ZVI mixture with bentonite, and they had some very successful results. And so I think one way to look at the bomber technology is sort of soil mixing light in this case. And so we went along with, we used a lot of the information that we gathered from the south plume. And so I would expect, given the positive results we're seeing at the south plume, that we would see similar results in the north plume.
Great, thank you. And one last question before we transition to Craig. How do you define well characterized, and how critical is characterization, initial site characterization, if you were to utilize the technology that you described?
Yeah, that's an excellent question. I would say, I mean, well characterized means you need to understand that confining unit, and you need to understand whether that site actually it has DNAPL. And so again, as I've mentioned, because these are vertical columns and they're typically higher permeability than the media surrounding it, they're going to be conduits. And so a confining unit is going to be sort of a necessity at any site. I would recommend potentially some geophysics work, but also just a fair amount of borings to understand what you're dealing with. A lot of soil work, a lot of collecting samples to understand the media that is in the subsurface. So I would, again, I caution. I think this is a great technology, but again, I caution the use of it in situations where a site, you may not know a whole lot about the site. It's something you can't just jump into.
Thank you so much, Steve. We'll get back to you with additional questions towards the end of the webinar, but it is now time to move on to Dr. Craig Devine, who is a vice president at Arcadis in Irvine, California. Craig has more than 20 years of experience remediating large groundwater plumes using a wide variety of technologies. He has developed and field-tested passive diffusion samplers for dissolved gas tracers, point velocity probes, partitioning interwell tracer tests, LNAPL tracer tests, nuclear magnetic resonance imaging, and low-temperature heating to enhance degradation rates for chlorinated solvents. Craig has his doctorate in geochemistry and hydrogeology from the Colorado School of Mines. Craig, please proceed.
Great, thank you, Rula. Appreciate the opportunity, everybody, to share with you about the horizontal reactive media treatment well, or HRX well. Before I begin, I'd like to acknowledge and thank my co-PI, Dr. Michelle Crimi at Clarkson University. All right, just an overview of the agenda. First, I'll spend some time talking about this HRX well concept, of what is it and how does it work. And then I'll highlight some features of the demonstration site, go through some of the treatability and design testing that was done ahead of field installation, and then walk through what was involved in the installation and cover some of the performance data, and then wrap up with some conclusions and takeaways. All right, so what is the HRX well? Essentially, it is a large diameter horizontal well, and when I say large diameter, I mean 6, 8, even 12 inches or even larger, that is installed along the groundwater flow path. And then it's filled with a reactive media or some other type of treatment media. So what's shown there in the cartoon, of course, the triangle indicates the water table surface, and the ambient regional groundwater flow direction would be left to right. And then you can see the well. In this case, we're showing a double-ended well. It's got both a surface expression on the in and outside, excuse me. And then it's constructed with 2 screens, one uphill and one downhill, and that center section, which is a darker gray, is cased and filled with a treatment media. So what you're doing is you're creating, or you're engineering, a high permeability feature, like a sand seam or a fracture, or probably more appropriately a karst feature. You're creating a conduit that has a much higher hydraulic conductivity than the surrounding formation. And that results in a flow focusing of groundwater into that feature. And then, of course, while it's in there, it reacts with the treatment media that's present, and then discharges as clean water. So in a sense, this is like a permeable reactive barrier, a PRB. And of course, as such, treatment in the aquifer down gradient of the HRX well follows some type of an elution curve, like shown there conceptually on the right, where there's a period of time after installation where nothing happens because the arrival of that clean water hasn't occurred yet, and then there's some sort of washout curve. And the reason, of course, water flows into a high permeability feature or in a well generally is because the head in that screen zone is lower than the surrounding formation. So really, one way you can look at this is that high permeability media within the HRX well sort of maps the low head on the right side into the upper screen on the left side. And so you've got really an extraction and injection well pair, but rather than treating water bringing water to the land surface and treating it and re-injecting, there's a treatment process in situ. And there are a number of, I think, advantages and distinctions to this technology. Of course, there are many solid phase reactive media that are currently available. And I think maybe something that differs from let's say a conventional trench-based PRB is that the use of the reactive media is very efficient. You're not wasting that. All that water gets focused and then is pushed through the reactive media. And what that means is that the amount of reactive media that's used is quite small, and therefore allows maybe more expensive media or designer media than you would normally consider for a conventional trench-based PRB. There's also the opportunity to use a treatment train approach. If there's some sort of pre-treatment needed or multiple contaminants, you could easily have multiple media types within the treatment zone within the HRX well. Of course, this is not limited to high permeability aquifers. In fact, we'll see in the next couple of slides, under a passive operation, the capture performance improves at lower permeability sites because you're able to maximize that permeability contrast, which maximizes flow focusing. The application isn't particularly depth limiting. We're currently looking at a site that is depth of water is over 80 feet. And while there are notable drilling costs, technically it's feasible. Of course, limited above ground footprint. You're not bringing water to land surface and no treatment systems above grade. Under a passive operation, there's minimal long-term O&M and energy requirements. And then I will note, for the field demonstration, we focused on this sort of passive hydraulic application, but there is a configuration where pumping can be used to enhance treatment, and I'll touch on that at the end of the presentation. So this equation is a simplified approximation of what the treatment width for an individual HRX well would be, and really it's a manipulation of Darcy's law. In the numerator, describes the flow in the HRX well. So K HRX is the hydraulic conductivity of the media within the HRX well. A HRX is the cross-sectional area of the HRX well, and I HRX is the hydraulic gradient within the HRX. And in the denominator, you have terms that similarly describe the characteristic of the aquifer. So you can see that, you know, the way that you maximize that treatment width is by increasing that contrast, by increasing the hydraulic conductivity of the media relative to the aquifer and maximizing the cross-sectional area. And if you're willing to assume that the gradient terms are approximately equal, which is the case for longer wells with long well screens, you can develop this sort of nomograph that relates aquifer hydraulic conductivity to the calculated treatment width on the y-axis. And this is log scale, and you can see the units there, and the x-axis are in feet per day, and in the y-axis it's treatment width. And the dashed lines are various well configurations. So I'll just, in this case, focus on that center dashed line where it says a 12-inch diameter well and an aquifer thickness of 20 feet. And so you can see that that treatment width in an aquifer that is very permeable under a passive application is quite small in the only single-digit feet per day, or excuse me, feet length. But as you decrease in average ambient hydraulic conductivity down below a foot per day or so, you start getting into treatment widths that are tens of feet. And so again, for lower, moderate to low permeability sites, the treatment widths can be quite viable from a cost effectiveness perspective. And then just a quick comment on the potential reactive media and target contaminants. There's a whole list of currently available reactive media that could be used to treat a broad suite of potential contaminants. In this case study, we use zero-valent iron to address chlorinated solvents. We're currently working on a system at another Air Force base where we're planning to use ion exchange resins to treat, to absorb PFAS. And then just a couple of weeks ago, we had an expression of interest from one of our mining clients about using barium sulfate for radium. So I think the point is that there's a lot of potential options. And again, because the media usage is quite efficient, we can start to consider media types that are relatively expensive and yet they still don't drive the overall project cost. So the field demonstration site that was selected was what's known as Site 3 at Vandenberg Air Force Base in Central California. The aquifer thickness is about 8 feet at a depth of 20 to 22 feet, so relatively thin, relatively shallow, and the average hydraulic conductivity is about 1/10 to half a foot per day, so low to moderate hydraulic conductivity with a low ambient hydraulic gradient. So sort of an idealized site to demonstrate and validate the technology. This is the first full-scale field application of this technology. Average groundwater velocity was less than about a foot per day. Pretty high TCE concentrations, both in the inlet screen area as well as just throughout the whole treatment and test zone, 1 to about 40 milligrams per liter parts per million. And on the figure on the right, the plan view, you can see the alignment of the HRX well, groundwater flow, sort of left to right. And you can see a blue zone, 2 blue zones with hash marks. Those represent the screens. And then, of course, the pink represents cased sections of the well. And if you look above the blue arrow by the groundwater flow text, you can see the outline of a tree in the aerial. And if you then look down to the photograph, you can see that same tree in the photograph. So the alignment of that well kind of comes from page left, underneath the people in the photograph, underneath the road, and then daylights sort of near the power pole onto the right. So I think a good example, this is a very active road, a good example of, from a practical standpoint, how this technology can be delivered and deployed under active infrastructure, and has the potential to have minimal impact to ongoing facility operations. This is just a quick summary of some of the treatability and design testing that was conducted. Really 3 types of general activities. One kind of class of activities was around optimizing that media. Of course, we were looking to maximize the permeability of that media, but you also want to make sure that the reaction kinetics are appropriate. So Rick Devlin and his team at University of Kansas conducted a number of column tests to look at a variety of ion types and understand the relationship between permeability and reactivity, and also longevity. So we ran well over 1,000 pore volumes to ensure we didn't see changes in permeability or reactivity over those times. On the photograph on the right, Rick also has developed what's known as a point velocity probe. It's a small scale tracer test system that can measure groundwater velocities in situ at a local scale. And he redesigned these so they could be deployed within the HRX well, so that we could actually measure the amount of flow focusing and the velocity in the HRX well. And then the tracer breakthrough curve there in the bottom is an example of some results from some pilot and mesoscale HRX systems that Michelle Crimmy and her team developed at Clarkson to further validate the concept and confirm the numerical tool, modeling tool that we use to support the design. This is a schematic of the actual HRX well that was deployed at Vandenberg. You can see again the aquifer thickness is about 4 to 8 feet. You can see the screen zone, flow left to right. There's that focusing. The total length of the well is about 550 feet at a depth of around 20 feet, a 12-inch diameter well. Based on the design modeling and the aquifer characteristics, our target treatment zone width was about 40 to 50 feet. And we had those PVPs that I just mentioned, those tracer test instruments installed both in near the inlet and outlet screens to measure flow. And they're actually in sort of those sand-colored rectangles, if you can see those. Based on the design modeling, our target residence time within the ZVI was 6 to 20 days, about 100 days total transit time between screens. And I think something I'd like to just again point out or underscore here, that the total reactive media usage was less than a cubic meter of ZVI. So again, very limited amount of ZVI. The total media cost was only a few $1,000s, and the majority of that was really related to shipping. I think I forgot to point out on this slide here, you can see also several blue squares, 4 on the left, 3 on the right. Those are the cartridges that were constructed that contain the ZVI. So the ZVI was really only in those 7 cartridges. And then we actually had blank screen in the middle. We didn't need the well that long, but there was a road above this section of the well, and so we needed to extend the well to get beneath the road. And I'll highlight these cartridges, but these cartridges were designed to be removable and replaceable. And here's a conceptual depiction of one of these individual cartridges that then go inside the well. Figure A and B sort of show the mixing of the ZVI with the sand and then the placement in one of these individual cartridges. Photographs C and D are some photographs of the actual cartridges themselves, and you can see on the end of the one in D a flange that allows multiple cartridges to be connected together. Photograph E was all the cartridges that were constructed ahead of time at the driller's workshop and then brought out to the site on a trailer. Photographs F and G were some cages filled with expandable clay bentonite that served as seals to make sure we didn't have short circuiting between the outer cartridge wall and the inner casing of the well. And then photograph H is basically a female coupler that allows with a male end adapter on the end of a drill string to push and pull the cartridge inside the HRX well. This slide shows a few photographs of the installation. Again, if you look on the top, you can recognize that tree I pointed out a few photographs before in the road. And then you can see the blue drill rig off to the left. And so the entry pit was sort of behind that white Conex box. And then the boring alignment goes, again, underneath the road, and daylight's on the other side of the road. You can see a number of those other roll-off boxes that contain drilling waste, primarily the drilling muds. Some photographs. It's a mud rotary system, and photograph B shows the drilling bit. The process is somewhat involved. There's a pilot bore that's drilled with that duckbill bit that allows real precise directional drilling. And then a reaming process occurs, which is indicated there in photograph C. You can see that actually it's an 18-inch reamer, and in that case, this is the last reaming run, and we're pulling the completed well string back through the hole. Photograph D shows tremie pipe that was used to put the grout seal around that center casing. And I'll just focus on photograph G is sort of the completed wellhead stick up at the end. And in this case, we had enough access that we didn't, that a stick up was fine, but it is possible to have construct a large vault so this could be installed subgrade. So now I'll move into some of the performance data. Again, if you recall, this is a passive system, but in some ways you could think of it as the uphill screen acts as an extraction well and the downhill screen acts as an injection well. And of course, what's coming out of the downhill screen should be clean water. And so I've got some groundwater elevation data from before the HRX well was installed, which is the photograph on the left, or the image on the left, and then 3 snapshots, several 100 days or so after HRX well installation. And you can see in black are the actual head elevations at the wells, and then the white lines are equipotential contours. And so you can see, of course, before the HRX well was installed, those water elevations are almost identical, really very flat gradient. And then after installation, you can see the effects of localized mounding. And I'll just comment that the degree of mounding was very consistent with model predictions and clearly shows water discharge from the HRX well. I mentioned that we installed PVPs to measure groundwater velocity in the HRX well. Our design model was hoping that within the well we'd have about 7.5 feet per day of flow. Again, recall the aquifer velocity is less than about 1/10 of a foot per day. Based on the PVP data, the average data was around 9.5 to 10 feet per day. So clearly validated the flow focusing and translates to about a 9-day residence time within the ZVI, which is consistent with the design model. So based on that updated hydraulics, this is our current interpretation model. Again, you can see the inlet and outlet screens in the top view there, and then a series of monitoring wells, one on the uphill side and 4 on the downhill side. And our calculations suggest that we should have about 52 feet of treatment width, again, which was consistent with our target of 40 to 50 feet. And all of those monitoring wells then should be within this zone that we should see the effects of elution or cleanup over time. So I'll just summarize the concentration data about a year after installation. Again, there's the HRX well alignment that shows the flow focusing, and on the uphill side, we've got a well that concentrations are about 30 to 40 parts per million during the treatment period. And then if you see that arrow right at the beginning of the screen of the HRX well, we have essentially no TCE coming out, so tens of ppm coming in, and then clean water with essentially no TCE, single-digit ppb levels coming out, so multiple orders of magnitude treatment. And that translates to a mass discharge reduction of 1.5 to 2 grams per day. And again, this is a technology that's designed for sort of long-term mass discharge control. And then the 4 performance monitoring wells that are within that expected treatment halo within the year time period. Of course, you can see the percentage reduction in all those wells, and they follow that general elution curve, where there was a period of time where the clean water hadn't arrived, and then an elution curve behavior through treatment. And on average, those wells currently are about 50% reduction in concentration. And I will make a comment. The drilling fluid that's used is a guar biopolymer that's biodegradable, and we saw notable cis-DCE in a few wells. We did do a fair bit of development, but some of that residual drilling fluid remains in place and is promoting biological processes in addition to the abiotic process with ZVI. That's been actually fortuitous because we've used that cis-DCE as a tracer in some wells to confirm when the arrival of that clean water actually occurred. But of course, over time, that process would be expected to decline, and the primary treatment processes would be the abiotic treatment of through the ZVI. Now, again, this was all of a passive application, and these passive scenarios, I think, are appropriate for sites where you have, again, low to moderate hydraulic conductivity, but at higher permeability sites where it might be difficult to get that contrast, there's a configuration where a pump could be used to enhance capture. And in this case, if you look at the conceptual figure, a packer is installed right at the beginning of the cased section, and then a pump is placed with the intake on the uphill screen on the left, and then rather than bringing that water to the land surface, that water is just simply pushed through the packer into the case section. So you're really just sort of enhancing flow. And we performed a conceptual test at this site where we increased well flows by about 2 times and saw, of course, hydraulic response in the aquifer. We saw enhanced draw down near the uphill screen and draw up or mounting in the downhill or the downhill screen. And I'll just highlight, in this particular scenario with that little bit of enhanced pumping, again, we're not talking about large flows and we're not bringing water to land surface, so the energy draw is very minimal. We were able to notably increase treatment zone size. So I think this has the potential to expand applications to more permeable sites. Briefly, I'll just comment on an alternatives analysis we conducted at the Vandenberg site. We compared the HRX well to more other conventional technologies that you would consider for long-term mass discharge control. Again, not aquifer restoration, but really long-term mass discharge control, and that would be a line of groundwater extraction treatment wells, or a funnel and gate-based PRB system, sort of a conventional PRB. And we looked at a number of typical screening criteria like overall protection of human health and environment, effectiveness and permanence, reductions in toxicity and mobility and volume through treatment, implementability, sustainability, and life cycle cost. And generally, these all compare favorably, but of course, the bottom 2, sustainability, the HRX well has some potential distinct advantages or higher potential for higher performance. And also life cycle cost was certainly consistent with the other technology, and actually maybe came out, the overall range came out a little bit lower. So I think in many settings, this compares quite favorable to conventional technologies. So in conclusion, this demonstration test verified the flow focusing hydraulics of the HRX well. And in this application, we're seeing 50 feet or more of treatment width under the passive operation. And you have near immediate contaminant flux reduction at the discharge screen of the HRX well. So like a PRB, almost immediately you're having mass flux control. And then, of course, performance in the aquifer downstream happens through time. We're seeing all performance wells exhibit treatment as expected. Also, the cartridge removal and replacement is very straightforward. As part of some of the testing, we mobilized a rig and pulled the cartridges out and pushed them back in, and they were quite easy to do. So we anticipate removal and replacement as needed is a straightforward thing to do. As I highlighted, the capture or treatment width can be enhanced by pumping, which expands applicability for high permeability sites. So the benefits of DoD, it's ideally suited for long-term mass flux or discharge control. Has limited footprint, energy, and O&M requirements. It's an in-situ treatment technology with no groundwater, no above groundwater management. Media usage is efficient, and there are many options applicable to challenging contaminants like chlorinated solvents and even PFAS. And we are, based on this demonstration project, the life cycle costs are quite favorable in many applications. So then I'd like to just close with a few acknowledgements. First, Kathy Gerber at Vandenberg and Hunter Anderson with AFCAC, Don Ely at the Regional Water Quality Control Board, and then a whole bunch of folks, Rick Devlin's team at the University of Kansas, Michelle Crimmy's team at Clarkson, our drilling partners at Directed Technologies Drilling, DTD, and then a number of folks at Arcadis as well. And with that, Rula, I'll hand it back to you.
Great. Thank you so much, Craig. We have received a number of questions for you also, and we're going to start with one that is from the Washington State Department of Ecology. Can you elaborate on how many square feet of access area are needed for the drill rigs when installing a horizontal well?
Yeah, that's a great question. I would say, the general access requirements are maybe a little larger than a conventional drill rig, and it depends on the actual length of the boring and the size of the rig you'll need. But I would say maybe 60 feet by 60 feet is probably appropriate in most settings, and then you would need some room for staging as well, equipment staging, but that doesn't have to be in the same location.
Thank you, Craig. This is a question from the Connecticut Agricultural Experiment Station. Can you explain why water should flow from the lower permeability matrix into your higher permeability horizontal well when it has to flow back out into the same lower permeability matrix?
Yeah, that's a great question. So what the HRX well does, like any high permeability feature, is that it, at least the way I think of it, it sort of maps or translates the lower head that's in the aquifer in the down gradient zone into the upscreen location. So in the aquifer, there is a regional gradient, and water levels near the outlet screen in the aquifer are lower than the water levels in the aquifer near the uphill screen, the inlet screen. And because the reactive media is so much higher permeability than the formation, that lower head, in a sense, is mapped very efficiently to that upper screen. So the actual head in the upper screen is lower than the surrounding formation. So again, just like a fracture or a sand seam where water flows in and then runs down that length and then flows out at the terminus of that high permeability feature, the HRX well sort of maps that low head. And then again, it's sort of like an extraction and injection well screen.
Great, thank you. This is a question from Jacob. Does your system have the potential of rapidly transporting contaminants down gradient if the treatment media, or should the treatment media become ineffective or is spent?
Yeah, that's a great question. Very insightful. So that is a sort of performance risk, right? You've created a hydraulic superhighway, and if that media isn't working, then you could shunt water, which could be highly concentrated from an upgrading area to downgrading area. So yeah, the primary way in which you would manage against that is to make sure you had an adequate performance monitoring program where you were monitoring water right in that outlet screen, and had performance goals that would, drive a change out schedule for the media. And of course, if for whatever reason that well needed to be removed, you could simply abandon it by filling it with grout, and that flow focusing aspect of the well just simply goes away, and the hydraulics revert to what they were before the HRX well was in place.
Great, thank you so much. How well might your technology work in a mixed permeability environment?
Yeah, good question. I mean, I think like any technology, as you get to more heterogeneous scenarios, the uncertainty goes up. We've done a little bit of modeling where we've put domains with pretty complex hydrogeology in and looked at effect upon treatment and capture. And I think in general, maybe again, if you go back to the extraction injection well analogy, that upper screen still has a lower head than the surrounding formation, like an extraction well. The reason water flows from an extraction well is removing water from the well with the pump, and that keeps the head in the well low, and so water flows into it. So if the head in the well is still lower than the head in the surrounding formation, you will have a driving force to bring water into that uphill side. And yet if you've got really severe permeability contrast and poor connectivity, you may have the potential for bypass flow. So I would say, like most heterogeneous sites, the degree of characterization you need to have reliable performance predictions is tied to the degree of heterogeneity. At this particular site, I didn't mention it, but as part of our pre-testing, we went out with an HPT system and collected very detailed hydrogeologic data along the well alignment and sort of in the general area, and that was used to inform our conceptual and numerical model. And I think a similar approach I'd recommend a similar approach at heterogeneous sites.
Great, thank you. Could multiple HRX wells be used together to address a plume that is wider or thicker than what you've described here?
Yeah, great question. So again, at this particular demonstration, the objective was to install a single well and look at its performance, including its treatment width. And in this case, the treatment width was 50 feet. And if you recall, I had an alternatives analysis table where we looked at scaling this technology up. And at this site, the total treatment width of the zone of interest would probably be about 150 feet. And so we conceptualized having 3 HRX wells sort of side by side at 50 feet of capture width each to address that. And again, you can sort of think about it the same way you would think of a series of extraction wells. If each extraction well has a certain capture width and you have a total capture width, target capture width that's larger, you would use multiple wells to achieve the overall system performance you needed. So you would apply them in a similar sort of way. And I'll make a quick comment that could also be applied if you had a very thick treatment zone as well. So not only wide, but thick. You might have HRX wells at various elevations conceivably.
Great, thank you. Okay, and here's a question from EPA Region 10. Was DNAPL present at your demonstration site at Vandenberg Air Force Base?
We don't believe in the zone where we were treating there was DNAPL present. It was not an immediate release area, but as you know from the concentrations, they were quite high in the ppm range.
Another question from EPA, Craig. What is the need for the second treatment media zone after the solid casing? For example, a figure on slide 47.
Right, yeah, insightful. Again, based on the estimated mass discharge and load from the upgradient screen and the column test, we anticipated a total ZVI needed, and that translated to those 7 cartridges. We could have installed them all on the uphill side or all on the downhill side. It really didn't matter. But because we had easy access for both sides, we basically split the cartridges up and put roughly half of them on one side and half on the other. And then also, if you recall, both sides had a PVP system in them, and those PVPs were placed in cartridges very similar to the treatment cartridges. So I would say it was sort of an arbitrary design. We could have put them all on one side or the other, but for practical purposes, we split them up and put half on each side.
Great, thank you. All right, well, it's time to pull Steve back into the discussion, and I'm going to ask you both a question and have you weigh in, and maybe we'll start with you, Craig. Based on the findings of your field demo, are there any improvements that you would make to your technologies moving forward before full-scale implementation?
You know, I don't know that wholesale there were major improvements. I think we did learn about the importance of the design modeling process. I didn't go into it here, but we did a lot of iteration between well diameter, screen length, actual placement, costs, and sort of went back and calculated treatment width. Sort of went back and forth quite a bit to optimize that design. So I think that's something I would carry forward, the importance of that task. Also, very important task is the media treatment selection. Very important to make sure you're maximizing that permeability and understand sort of that long-term reaction kinetics. So I would say we thought those tasks would be important going in, maybe coming out of it. We realized even more so than we anticipated how important those efforts are on the front side.
Great, thank you. Steve, can you please address this as it relates to your technology?
Yeah, sure thing, Rula. So in terms of improvements, I'd mentioned this earlier. I think one of the current limitations of the bomber as it stands, and again, the goal of the project was to simply take the bomber as is and repurpose it. But obviously there's some changes that could certainly be made that would benefit. And one is, you know, the amendment plate and placement right now is from bottom to top. And so that's really not an efficient use of your reactive media. At site 17, it didn't matter so much because the contamination is actually extending from about 5 feet down to 30. And so that there was only a little bit of material loss. But at other sites, obviously, there'll be a tighter treatment zone where we would want to focus that ZVI mixture on that treatment zone and not waste it in locations that are above or above that. And so that can be done by just some adaptations to the equipment. Perhaps it's 2 Elkin mixers or 2 delivery systems, one where we can time it as that mandrel is moving up to figure out when to switch over from one source material to another. And that other source material could be a simple filler like a sand, or it could be a bentonite mix of some sort that could kind of cap these columns.
Great, thank you. And both of you talked about today advances in remediating groundwater contaminated with chlorinated solvents, and in both cases, you described the use of amendments to accelerate the remediation of chlorinated solvents. So maybe we could end with a short discussion on your favorite amendment, so as to speak, or what you've seen based on your R&D work, what works best in the environments that you described. Steve, can we start with you, please?
Sure. Talking strictly with the bomber, again, the viscosity of that you know, mixture is going to matter. Just the way the composition of it will matter. But in general, I mean, there's a variety of different remedial amendments that could be mixed with a sand or any other kind of filler. Chemical oxidant, maybe a persulfate could be used. Another option here would be a particulate carbon amendment could be used in these columns, so as a sorbent. That's another application. I wouldn't say I have a favorite. I guess it's really dependent on the type of site that you're dealing with. And I think right now, I think the ZVI worked very well with the bomber technology, and I don't see any reason why these other amendments wouldn't be as successful in terms of the delivery.
So you're saying it's really dependent on the site geology and hydrogeology and contaminant footprint, not as much as dependence on the technology beyond the viscosity issue.
That's exactly right. I mean, when it comes to amendment selection, in terms of the use of the bomber, it's going to still be a decision made based on what's best for the site. I think that we can adapt an amendment to the bomber technology and vice versa to make something work.
Great. And Craig, what amendment works best with the technology that you described, the horizontal wells?
Yeah, good question. For this demonstration site, we started with something pretty conventional, ZVI to treat TC. And we did that for a number of reasons, but mostly we just didn't want to introduce a more complicating variable in the process. But I think there's opportunity to optimize that amendment a little bit further. In fact, we're in the design process for another site, another TC site, but we're looking at a sulfidated ZVI, which has a faster reaction kinetics, and it's a more efficient, less hydrogen generation. And then we're also sort of side by side looking at some of the slow release oxidant solid phase reagents and whether that could be configured to be in an HRX well. And we're planning on doing some treatability testing around that to sort of look at those questions. So I do think there's some improvement opportunity. I think what that could translate to in terms of the HRX well design is you might need even less treatment time, less residence time within the HRX well, which I think particularly for the active configuration where you might be pumping, the residence times in those scenarios can be quite short. So I think there's some advantages there. And of course the oxidation technology also has very fast kinetics. While you'd probably have to balance that against a replacement frequency, there may be some overall benefits to that approach. But I think, generally that's going to be a pretty site-specific analysis.
Great, thank you so much. At this point, I'd like to thank our speakers for a fantastic job delivering the content here, and also our audience for being very engaged and asking a lot of great questions. I'd like to remind you all that our next webinar, kicking off the new year, is on Thursday, January 23rd. It's in the Installation, Energy, and Water Program area, and it will detail results from DoD research efforts on battery storage resiliency from installation microgrid simulations. The webinar will also focus on opportunities for field demonstration. This event will feature two speakers, Dr. Jeff Marquesi from the National Renewable Energy Laboratory and Mr. Craig Schultz from ICF. Registration is open, so please visit the SERDP and ESTCP webinar webpage to register for this and other future webinars. Before we conclude, I would like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would appreciate it at this time if you could please take a very short moment to complete the survey that will pop up on your screen. This concludes today's webcast. Thank you so much for your attention.